Yeah. Uh-huh. Uh-huh. Okay. All right. I gotta go. I gotta record a video for AP Physics. Okay. All right. I love you too. Bye. Sorry about that, guys. Had to take a call. Um, this is the third video. We're going to learn about electric potential, which is a concept more closely related to energy than anything else in electrostatics. I mean, it is energy. Okay. Last year we kind of we waved our hands a little bit about like how we define electric potential, and this year you can actually understand the calculus a little bit better because most of you are in calculus. So the way that we talk about electric potential, what it means and where it comes from, is we start with definition of work. Work is the integral of force. If you're talking about electrostatics, then your equation for force, the most basic one, is QE. The reason that's the best one to use is because the electric field is not always going to be kq over r squared. If you recall from when we did Gauss's law last year, the electric field is not always kq over r squared. It could be over r, or it could even be like a uniform thing, like if you've got, say, a plate. Okay, so a plate, a cylinder, a sphere all have different electric fields, and therefore this is actually the best way of talking about the force acting on some little test charge. All right. And then I replaced work with negative delta U because the work that's going to be done by an electric field is going to come at the expense of the potential energy due to that electric field, because electric fields are conservative forces. Okay, so we can say work equals delta K, and also delta K equals negative delta U, right? Any increase in kinetic energy comes with a decrease in potential energy. Okay, so work then is negative delta U. Moving that negative sign over and dividing by Q, we get this. And that is the definition of potential. All right, so potential is usually measured in volts. But if you remember what a volt is, it's a joule, because that's the unit of energy there, per coulomb. So it's a joule per coulomb. And so in the case of something like a 1.5 volt battery, here's my best drawing of a battery, best ever. Okay, so if you've got something like a 1.5 volt battery, which is like a AAA or a AA or a D cell, and they're all 1.5 volts. What it means for it to be 1.5 volts is that there's 1.5 joules of energy stored in the battery per coulomb of charge that it moves. Later on, we'll talk about amps, right, when we do current and stuff. Amps, if you recall, is a coulomb per second. 1 amp is a coulomb per second. So if you have a 1.5 volt battery that's also, say, producing 1 amp of current, that means that it has 1 coulomb going through it each second, which means that it's doing 1.5 joules of work per second, if you like. All right, the more central concept at this time is to understand the relationship between volts and potential energy and charge. The amount of energy that a particular number of volts gives you depends on how much charge you move. So if you've got a 1.5 volt battery and it moves 1 coulomb of charge, it did 1.5 joules of work on that 1 coulomb. If it moves only a half coulomb, then it only does 0.75 joules of work. All right, and so you may see questions where it's like, here's a charge, and the potential here near it is like 4,000 volts, and the potential over here is 2,000 volts. I should have picked different numbers. Let's pick a little further away and call it 1,000. There we go. All right, and so if a charge were to move from here to there, it moves through a potential difference, delta V, of 1,000 minus 4,000, and that's negative 3,000. all right, which means that the change in potential energy for some charge moving from here to there would be Q, this Q, whatever the little Q is that's moving between those 2 points, all right, times negative 3,000, and that would mean that it would, say, lose some amount of energy, some amount of potential energy, which means that it would gain that amount of kinetic energy. Okay, so a volt is not a specific amount of energy. It's a certain number of joules per coulomb of charge that you actually move. In this case, it's negative 3,000 volts. All right, fine. And that means it's that many joules per 1 coulomb that you move. So if you moved a whole coulomb, that would be a decrease of 3,000 joules of potential energy, electrical potential energy, and an increase in 3,000 joules of kinetic energy. All right, fine. Back over to here. This then is our definition of what voltage is, and we'll use that throughout this unit in a variety of contexts. Okay, but the idea that it's the integral of electric field is pretty essential. We'll also talk about the reverse relationship where electric field is the negative derivative of potential, which is actually kind of related to that equation you might remember from last unit, which is that force is the negative derivative of potential energy. They're very related, as it turns out. Okay, let's see then. All right, if what you have is a point charge, then the electric field is kq over r squared. All right. If you took the integral of that, you would get this very familiar formula for the potential due to a point charge. You may, at this point, have like a mental hand raise, like, Mr. Errico, you've been saying potential difference, like, which one is it? Why is it delta V right here, and then suddenly it's V right there? All right, potential difference relates to the change in potential between two specific points. Potential relates to the potential difference between this point and infinity. You saw how my hand went off the screen. It's over there. Infinity's way the heck over there. All right. So potential is the potential difference between infinity and whatever other point you happen to be talking about. In other words, it just means that you take this integral with bounds of infinity to wherever you like. All right, now, how much of this do you actually need to comprehend in order to do the homework? Not a lot of it, but you need to write this down somewhere because we are going to need it when we start doing things with like Gauss's law and finding potential near something like a charged cylinder. Okay, so this is going to be very important in a little bit. As for like why the bounds are infinity to r, that's something that we'll cover in a little bit. Why would you start at infinity? Why don't you start at the nearer position? It's part of how it's defined. Okay, so we'll get to that when it becomes important. All right. So the main thing that you need to know for the homework and for understanding the rest of the video is this equation right here. Potential is just kq over r. Fine. No vectors because energy is a scalar. So there's no r hat here, right? They just add or subtract based on signs. So if you have, say, two charges and they're both positive, all right, they both produce a positive potential near them. Doesn't matter where you put them. All that matters is how much charge and how far away it happens to be. So positive charges make positive potential. Negative charges make negative potential. That's how it goes. All right, as an example, let's look at this question right here, where I've got a Q, a negative Q, and another positive Q. They're separated from each other by distances of d, and we're going to be asking a bunch of questions about the potential at various points along the x-axis. Let's actually move that. There we go. All right. So the first question that's going to be asked is, what's the potential at 3/4 D? Why 3/4 D? That's such a strange question, Mr. Erico. Because the math was nicer, is the short answer. Okay? So if 3/4 D is like, let's say, right there, that's about right? Where D is this distance and that's 3/4 D. In order to work out the potential at that point, we've got to figure out how far each of the charges are from that point, and then we just add up all the various potentials. So that's going to look like just sum of KQ over R is going to be the potential. All right, let's start with the negative one because that's the easiest. The potential due to the negative charge is going to be negative KQ over 3/4 D. So I picked that one because I didn't have to do Pythagorean theorem. Also notice the potential for that one is negative because it's a negative charge. And that's the entire reason why. Negative charges always produce a negative potential around them. All right. For the two positives, we're going to have to figure out what this distance is, which means some Pythagorean theorem. So let's see. Square root of D squared plus 3/4 D squared. That's going to give us 9/16. All right, if you're looking at that and you're like, ooh, I don't know how that would simplify. That's just going to be an ugly thing we're going to carry around. No. I made it nice. Let's get a common denominator here, right? This is 1D squared, which could be expressed as 16/16. 16/16 plus 9/16 would be 25/16. All right, and if I take the square root of that, it's going to be 5/4 D. So this and that are both a distance of 5/4 D away. All right, so I picked it so that the math would be a little bit nicer. All right, since both of those are the same distance away, we can just go ahead and say they'll both produce the same potential at that point. So I'm going to say it's 2KQ over 5/4 D. And there we are. I mean, nearly, right? We've got to do some stuff here, like, how about I multiply top and bottom here by 4 to get rid of the ugly fraction over a fraction. And same idea here, so 8KQ over 5D. And let me pause the video so we don't waste time. We'll just combine fractions. And there we have it. 4KQ over 15D is the potential at this particular point along the x-axis. All right. Part B wants to know it says the final kinetic energy of a charge plus Q that starts at that position. All right, well, if it's the final energy, they must be implying that it's going to go all the way to infinity. What is the potential at infinity? Always zero. Always zero. So it's going to somewhere where the potential is 0. So if I wanted to know the kinetic energy at that position, I would start with a couple of assumptions. Number one, delta K is negative delta U. That's probably a pretty good one. I can get a little bit sloppy with signs here because I know it's going to have positive kinetic energy when it reaches there. Okay, so I'm just going to say the final kinetic energy, since we're assuming it starts from rest, is going to be Q delta V. And here's where I'm getting a little, actually, let me be formal with signs. Negative Q delta V. The change in potential is going to be final minus initial. That's 0 minus this, which means that it's going to be negative that. So when all is said and done, it's just going to be Q times that. Okay, so 4KQQ over 15D will be the kinetic energy, and I could turn that into a speed if I like. All right, we'll continue in part 4.